Welcome back, everybody. We're going to finish talking about Chapter 8 by focusing on Section 8.3. And specifically now, we're going to talk about population proportions and how we're going to estimate those values. And like before, we will compute margins of error and also confidence intervals. Let's jump right in. You're going to see that this section is very similar to the previous section when we were dealing with sample means and trying to learn about population means based on those sample means. So for example, when we were talking about estimating population means, you're going to see how all of these things that we talked about previously are going to just change so that they can fit population proportions. So instead of estimating population means, now we're estimating population proportions. Previously, we computed a margin of error based on the formula for computing margin of error for means. And that was based on standard deviations for means. You're going to see that this is going to change just a little bit based on proportions. So here we have 2 times the standard deviation that we learned previously for proportions. Same thing when we're computing confidence intervals. Previously, we were computing 95% confidence intervals around a sample mean. We would add and subtract the margin of error. Of course, now this sample mean is going to change to a sample proportion. And now when we kind of look at it graphically, we took the sample mean, we added the margin of error to that value, and we subtracted the margin of error from that value. Now we're going to start out with the sample proportion, add the margin of error, and subtract the margin of error. So everything is really very similar. It's just that we change our focus now from a sample mean to a sample proportion because we're not trying to learn about the population mean. We're trying to learn about the population proportion that is represented by that sample proportion. All right, let's go through an example where we will compute the margin of error and confidence interval, a 95% confidence interval, based on some Nielsen TV viewer rating survey data. So a Nielsen TV viewer survey based on 5,000 randomly selected households estimated that 72.3% of the viewing population watched some recent World Cup soccer game. So we're going to compute the margin of error and a 95% confidence interval based on that sample estimate. Because remember, we want to figure out what's the population proportion of people who actually watched this game. What's the real answer? We know the value based on this sample of 5,000, so it's an estimate. And we also know that every sample is going to be different from the next. Well, we can quantify how different those values are by computing our margin of error. So let's go ahead and do that. We see it's based on the standard deviation for the proportions. We're going to multiply that by 2 because we know that within 2 standard errors, 95% of all sample proportions will fall. So that's why we're going to be able to plug that into our 95% confidence interval. So that's where we're going. So let's go ahead and compute this margin of error. So we're going to want to take 2 times this entire fraction in here. So 2 times the square root of our sample proportion. 72.3% would correspond to a proportion of 0.723. We want to multiply that by 1 minus that proportion. So 1 minus 0.723. Let's figure that out. 1 minus 0.723 equals 0.277. 0.277. Okay? And we want to divide that by our n. And our n was based on 5,000 viewers. 5,000. All right, let's do a little bit of simplification in here. Again, we have 2 times the square root of this fraction. Let's figure out what the numerator equals. We have 0.723 times 0.277. Well, 0.277 is already in my calculator, so let's multiply that by 0.723. That equals 0.2002. Let's just call that 0.20. So 0.20 divided by 5,000. Okay? Now let's go ahead and work that out a little bit more. So we're going to have 2 times the square root of 0.20 divided by 5,000. Let's figure that out. 0.20 divided by 5,000, that's going to be a very small number, equals 0.00004. So that's, let's see, 1, 2, 3, 4 zeros and then a 4. So we're going to need to use all those numbers, otherwise we'd have a 0 in there. So 0.00004 All right, and we can get rid of that really quickly by finding the square root and moving on. So let's just kind of bring ourselves down here for a second. Let's find what this value is. We're going to have 2 times whatever this value is in here. So we're going to find the square root of that. I've already got it in my calculator. We'll hit our square root button. That equals 0.0063. Let's use that, 0.0063. So 2 times 0.0063. And let's figure out what that equals really quickly. So 2 times 0.0063 equals 0.0126. We'll round that to 0.013. 0.013. Now, typically in our class, as you've learned, we round to 2 decimal places, but there are times that we can't. I mean, obviously here, we had to go out to this 5th decimal place because everything else was a 0. So we're just taking things as they come and we're being flexible. So we were able to round off our margin of error to 0.013. All right, well, let's use that now for our 95% confidence interval. So we're going to take our sample proportion equal to 72.3%. So we've got 0.723. Remember, we're always dealing with these in terms of proportions. So 0.723 plus 0.013. We're obviously here working on our upper confidence interval because we're adding that margin of error to our sample proportion. Let's work that out real quickly. We've got 0.723, and we're going to add to that 0.013. That equals 0.736. 0.736. So that's 73.6%. Let's now work on our lower confidence interval. That's 0.723 minus 0.013. Let's see what that equals. So we've got 0.723 minus 0.013. That equals 0.71. 0.71, or of course 71%. All right, let's go ahead and interpret this. I'm sorry, let's go back to our slideshow. Let's interpret what we have here. Remember, we have 3 important functions, 3 important factors essentially in our interpretation. So the probability level is one of them. We're working on 95% confidence intervals. So the probability equals 0.95. In other words, we can be 95% confident that between 71% and 73.6%, let's just round that off to 74, 74% of the viewing population was watching World Cup soccer. Okay, so we can see here, based on computing our margin of error, including our margin of error in our 95% confidence interval, we can get a good idea of what the true population proportion is by computing that range. So 95% of the time, using this strategy, our true population proportion will be within that range. All right. Let's look at another example. This next example has to do with political polling and the most recent presidential election that we had. A recent poll of 400 randomly selected likely voters found that 55% favor Romney over Obama. Compute the margin of error and a 95% confidence interval based on this sample. So this was just one poll that was conducted back during the election time. We're going to compute our margin of error, and once we find that margin of error, we're going to stick it into our formula for computing a 95% confidence interval. So let's go ahead and compute just like we did before. We're going to take 2 times this standard error right in here. So we have 2 times the square root of our sample proportion equals 55%, so that's 0.55 multiplied by 1 minus our sample proportion. 1 minus 0.55 would equal 0.45. And we divide that by our n. Our n is equal to 400. Okay. Let's simplify and solve here. We're going to focus on our numerator. So we're going to have 2 times the square root of this value in here. 0.55 times 0.45. Sorry about that. Let's find our calculator. We have here 0.55 times 0.45. That equals 0.2475. Let's just round that to 0.25. There we go. 0.25 divided by 400. Okay. Let's see what we get there. In this case, we're going to have 2 times. Let's figure out our fraction in here. 0.25 divided by 400 equals 0.00625. Let's just go ahead and take the square root of it real quickly. Knock this whole thing out. Square root of that equals 0.025. All right, so we have 2 times 0.025. Let's work on that real quickly. 2 times 0.025 equals 0.05. 0.05. All right, so that's going to be our margin of error. So now to compute our 95% confidence interval, we're going to take that margin of error, add and subtract that from our sample proportion. 55% favored Romney, so that's going to be a proportion of 0.55. So let's work on our upper confidence interval value. 0.55 plus our margin of error of 0.05 is going to equal 0.60, or 60%. 0.55 minus 0.05, as we work on our lower confidence interval value, is going to equal 0.50, or 50%. So we're trying to compute in here the actual true population proportion who favor Romney over Obama. We have here our confidence interval. Let's go ahead and work on the key factors as we interpret it. So the probability is 0.95, or we can be 95% confident that between 50% and 60% of the population of likely voters favors Romney over Obama in this particular poll. All right, so we can see that this range helps us understand what a potential value is for the true population proportion. All right, let's go ahead and take this just a step further like we did previously and talk a little bit about choosing sample size. Like I said before, when we plan studies, we often know the margin of error that we'd like to have. Because look at this last example. It's very rare that in a political polling type of study, we want a margin of error that is this large, 5%. We usually want our data to be much more tight in essence. I want my sample data to come closer to measuring the true population data. This is going to be off by plus or minus 5%. What if I wanted that to be a smaller number? So I can figure that out by manipulating my sample size. So we can estimate the sample size needed to ensure any margin of error by solving for the margin of error in our formula. So again, we just manipulated our formula to now solve for the margin of error. All right, well, we will use these formulas to figure this out. And you can see here, this is our formula for margin of error. If we just kind of flip it around, I'm able to find an approximate value for n by taking 1 divided by our margin of error squared. So this is the margin of error that we'd like to use. If we square it, take 1 and divide by that value, we will find the sample size that's needed. Let's go through an example and you'll see exactly what I'm talking about. So let's say you plan to conduct a survey to estimate the proportion of students who carry a cell phone daily. How many students should be in a sample if you want your confidence interval, your 95% confidence interval, to have a margin of error no more than 4%? All right, let's use our formulas. In this particular case, we're going to take 1 and divide by the margin of error that we want squared. So we're going to take 1 and divide by the margin of error that we want is 0.04. 0.04, and we need to square that. So let's work that out real quickly. We'll have 1 divided by, let's see, 0.04. Let's square that by multiplying by 0.04. That equals 0.0016. So again, we like to go out to 2 decimal places when we can. We can't in this particular instance because the number is so small. Let's work out that value real quickly. So let's take 1 and divide by 0.0016. That equals 625. So what we've learned here is that to ensure a margin of error no more than 4%, you'd need to include at least 625 students in your sample. You see, this is a really handy formula for determining our sample size given some particular value for margin of error. Let's go through another example. Yankelovich Partners is a really large name when it comes to polling research, for international polling and marketing research, stuff like that. A recent poll found that 61% of all households have a computer, with the margin of error equal to 3.5%. Approximately what sample size must have been used in this poll? Well, we can figure that out using the same formula. Let's say we want a margin of error of 3.5% or 0.035. If we stick that into our formula right here, we can figure out the sample size that is needed. So we're going to take 1 and divide by 0.035 squared. All right, let's do the basic math. So we'll take 0.035 and square it by multiplying by 0.035. That equals 0.001225. So we've got this big nasty number. Let's go ahead and just stick that in this particular case, because we will get a much more accurate sample size estimate in this particular case if we use all those values. 0.001225. Okay. All right, now let's just work that out. 1 divided by 0.001225 equals 816.33. 816.33 people would be needed in this particular poll. Now, of course, we can't have a third of a person, so we're going to just round that up. So to ensure a margin of error of no more than 3.5%, they would have needed to include at least 817 households in their sample. So this is a really nice method for estimating the number of people we would need in a sample to have some given margin of error. And as you, I assume, understand by now, the more people we have in our sample, the lower our margin of error will be. And the more people we have in our sample, the better our sample estimate will come to our population proportion. All right, everybody. That was the key content from section 8.3. For now, that is all.